Good morning all, and welcome to the fifth day of the 6-day workshop on OpenFOAM. This is Payal again, welcoming you all today. And today we'll be having the session on Magnetohydrodynamics by Professor Abhishek Ranjan of IIT Bombay. So, sir, over to you. You can start the session.
Yes. So this is a recorded lecture just for this particular FOSSEE seminar. It is about 33 minutes, and after that, I wanted to have sufficient time for question and answers. So in case you have any doubt, I would recommend that if you have a pen and paper with you, that's the best. Please make a note of the doubt, and maybe it's best to wait till the end, and you can mention the slide where you have a doubt or the context. So let me start this then, and yeah, and at the end we'll have the Q&A where I will clarify any questions or any doubts. So, yeah, and after that session, then there's another recorded lecture in 3 parts. So there's a 3-part lecture in the part 2 here, where he will demonstrate how to use the OpenFOAM software's existing libraries in OpenFOAM and how to build some new libraries with a different formulation called potential-based formulation. Welcome to the lecture on MHD. This is a 2-part lecture, and the first part is a brief introduction given by myself, Abhishek, from Mechanical Department, IIT Bombay, and the second part will be given by my student Swapnil, who will talk about how to compute MHD flows using OpenFOAM. So a couple of examples to motivate the topic are shown you pictorially on the left hand side. So the top shows the geophysical astrophysical example where you see the sun and sun's coronal mass ejection, CME, which hits the Earth's magnetic field, the solar wind essentially, and if the Earth's magnetic field was not there, that would essentially destroy a lot of communication system that are present. So it's of interest to a lot of astrophysicists to understand what is the physics in the solar wind, for example. That comes into the domain of MHD. And the second example is from engineering, where I show you the nuclear fusion experimental reactor. It's called ITER in France, where they are trying to do fusion experiments, and they hope that if it's successful, they will be able to produce a lot of power at very cheap cost and hopefully also in a very renewable and clean way. Now this is a brief outline of the topic. I will just give a brief overview, after which I will talk about the important assumptions and approximations, and then I'll talk about the induction equation and some non-dimensional numbers, and finally I'll mention something called inductionless or potential formulation, and that is very important in engineering, and some applications, and then I will finally end the talk. Now what is MHD? Now MHD is magnetohydrodynamics, but the better term is magnetofluid dynamics, because the word hydro essentially means water. It's the entire community of fluid, including liquids and gases, for which MHD is equally applicable. Now essentially the basic idea is that there has to be a mutual interaction of a fluid which is conducting in the presence of some applied magnetic field and applied currents. So the fact that the fluid is electrically conducting is very important, and also important is the fact that there has to be a magnetic field or electrical current present. Now as you are aware that the major equation in fluid mechanics is called the Navier-Stokes equation. It's the second law of motion, conservation of momentum. Now there in MHD what we have is body force term is the J cross B by rho, which is essentially the Lorentz force per unit mass term. Now this J and B are variables which may look a bit new to you. So J is called current density and B is called the magnetic field. So these are the two ingredients, and essentially the cross product is what leads to some acceleration in the fluid flow or retardation depending on the sign. So a non-zero value of this J cross B is an essential requirement. Now you can think about what all can make this J cross B non-zero. So of course non-zero J and non-zero B, but also the non-zero cross product. Those 3 things are required. Now apart from the Navier-Stokes, we also need the Maxwell's equations. These equations are essentially shown here. Now in that we will make some approximations which will make these equations a little bit simpler, and we will see in what framework those applications are essentially valid, and after that we'll arrive at list of equations which are called MHD equations, where you will see a slightly different form of the Maxwell's equations, a more simplified version, and of course you will see the Navier-Stokes equations once again. Now we also have the Ohm's law. So the Ohm's law is shown here, this equation at the bottom. J equals sigma E times E plus U cross B, and this E is electric field. So electric field is minus of gradient of electric potential. So now this equation, I said, is Ohm's law, but in case you're wondering, that Ohm's law that you may know about is V equal to IR. It is basically the same equation that now mentioned in a vector notation. Now if you write the vector J, which is current density, as current divided by area, and then you can write the conductivity also in terms of the resistance and the L and the A. If you do that, you can arrive at V equal to IR. So it's basically the same equation. There's an extra term present here, U cross B, that essentially has to do with the fact that in the electromagnetic induction there is a current which arises in order to oppose the changing magnetic field. It has to do with the Faraday law. Now I mentioned about the MHD arising because of a mutual interaction of velocity field and magnetic field. Now what do I mean by that? So this particular type of MHD needs the presence of an applied magnetic field. Now suppose you think about a moving fluid. If there is a moving fluid in the presence of a magnetic field, and if they are not parallel, that means there will be an EMF which is induced, and that results in a current which is sigma times U cross B naught. Now this induced current, which is a new current arising because of the phenomena conducting fluid moving under the presence of a magnetic field which is not parallel. This induced current is linked with a small b, which is a magnetic field, which basically changes the existing field. Now it's the total field which now interacts with the current to produce a Lorentz force, which is in this case small j cross b, and this Lorentz force being a body force term in the momentum equation, it affects the motion, so it basically changes the velocity field. This is shown here in the picture. You have a couple of poles in a magnet, and there's a conductor which if it starts to move towards the right side because of an external force F. Now what that does is it changes the original magnetic field. So you can see a small change in magnetic field arising, which is basically there to oppose the motion of the conductor. The Faraday's law is what is active here. Now the Lorentz force which arises is this J cross B. This should be a small j here. It essentially opposes the F. Now just imagine that you replace the solid conductor by a liquid metal which is typically very highly conducting. There in that case we have the electromagnetic equations along with the fact that there's a fluid and there's a force acting on the fluid, and as you know that fluids are deformable, which is what makes the topic very complex sometimes, but also very interesting at the same time. Now there's another avatar of MHD, if I can use that word, which in this case it doesn't need a fluid to be moving initially. If there's a still or a quiescent fluid and you have a large current which is applied, then that current with its own magnetic field which can create a Lorentz force. So that Lorentz force is basically a source term in the momentum equation, and that force is sometimes not balanced by the pressure gradient force, which is also a term in the momentum equation. Now whenever it's not balanced, this can initiate the fluid flow. Now this is pictorially shown in the schematic where I have a point current entering from here, and the current diverges, so it goes in all these directions radially outward. In this particular situation, it so happens that the pressure gradient is not able to balance the Lorentz force, which happens to be non-conservative in this situation. Now it is this example which sort of is an example of the situation where the MHD because of a current can also arise. So now if you have a fluid flow, this will have a EMF, and because of which we'll have a current once again, just like we had in the previous slide. That current will have its own magnetic field. Now it so happens that sometimes the induced current small j is very small, and it can be ignored. So those are some situations which are quite easy to handle comparatively. But if it's not the case, then the total Lorentz force, which is sum of both currents cross product with sum of both magnetic fields, must be considered. Now what is the MHD approximation? So first approximation is the same one that we made in fluid mechanics. We assume that the fluid is a continuum. We also assume that the charges travel at conductor speed, which means we neglect something called Hall effect. We also neglect something called displacement current, which is the dou by dou t of electric field. In case you forgot, this is the current which is essentially there inside a capacitor, which is filled with a dielectric. So in this case, this displacement current is ignored. We also ignore the electrostatic force or electric force. So if we don't ignore it, it becomes electrohydrodynamics. Because this force is ignored, it becomes magnetohydrodynamics. If you want to get more details about these approximations, you can look at textbooks, and I have a list of them at the end. Now, with these approximations, the equations become a bit simpler in a sense that now you see that the term with electric field derivative in time has vanished. You don't see any charge density terms. So in that case, those are some simplifications which have arisen. Once again, you see the Ohm's law and the Lorentz force written as J cross B. So J cross B divided by rho is Lorentz force per unit mass. But J cross B is nothing but Lorentz force per unit volume. Now let me just give a little bit of a background of what do I mean by these approximations. They are also called low frequency approximations. Now they call low frequency approximations because if you look at this time derivative, it is 1 over time, which is like a frequency. So if that is ignored, it is like a situation of low frequency approximation. Now one can do a very quick scaling analysis of the various terms present in the Ampere-Maxwell's law, and with that it's easy to verify in which situations it's possible to make the low frequency approximation. Because if we know that, then we will know where we cannot make this approximation also. So essentially I take the Faraday's law, and I am writing it as electric field by some length scale, which is of the order of frequency times the magnetic field. And if I replace this in this ratio of the two terms that you see at the top, this helps me obtain ratio in terms of the c square, which is nothing but light speed, and f square is square of the frequency. C square is the square of light speed, and d square is a square of a length scale. Now if c is very large, which as you know is quite large in most of our applications, in that case it is safe to assume. Similarly, if f is small, then even then it's safe to assume that the term below is much smaller than the term above, and therefore it can be ignored, making these equations Ampere's law. This term which we have ignored is called Maxwell's correction. Now let us look at how do we obtain the so-called magnetic induction equation, or the main governing equation for MHD. So we start with the Ohm's law, and in that we take the curl on both sides. So we have a curl of J, and then assuming the sigma to be constant, we have a curl of E and curl of U cross B. In that, on the LHS we use Ampere's law, on the RHS we use Faraday's law, replace the terms, and then we use the vector identity with div B equal to 0, and lo and behold, we arrive at this equation where this term lambda is nothing but 1 over mu sigma, and this is also called magnetic diffusivity. Now this has the same dimensions as kinematic viscosity and thermal diffusivity, so that's quite interesting. And now you can use some more vector identities and use the fact that the fluid is incompressible. We can obtain this equation, which is also called the induction equation. Does this equation remind you of a very important equation in fluid mechanics? You can pause the video and you can think about it. So I think it's a good time to just pause and get some feedback so that this also becomes interactive. Is there anyone who would like to pitch in and answer the question I posed here. So the question I posed is, this equation that you see in the gray box, does this remind you of any equation that you know?
Navier-Stokes equation.
You are close, but
Momentum equation.
momentum equation doesn't have a term which looks like this, right? It doesn't have a term which looks like this. So there's another equation which you can obtain from momentum equation. Anyone? So have people heard about the word called vorticity? Does that word mean anything? Vorticity?
Yes, sir.
Yes. So there's an equation for vorticity which you can obtain by taking a curl of the momentum equation, and that equation looks exactly like this equation, the equation for magnetic field, except that the B is now magnetic field. It was vorticity in the other equation, vorticity equation, and the lambda is now magnetic diffusivity. Whereas in the vorticity equation, because of the fact that we obtained from momentum equation by taking a curl, we have a nu there, kinematic viscosity. So in case you want to learn more about vortex dynamics, what I recommend is that there's a book on fluid mechanics by Kundu and Cohen, and there's a full chapter dedicated to vorticity dynamics. Learning fluid mechanics without vortex dynamics is kind of incomplete learning, in my opinion. So I recommend that very strongly to you. Okay, so let us resume then. The answer is that it resembles the equation for vorticity. So it resembles the vorticity conservation equation, where instead of lambda you have the nu, kinematic viscosity, and instead of B you have the vorticity, of course, but the other terms are exactly the same, and therefore the interpretation of the various terms is also exactly the same. The first term is local change in magnetic field. Second term is advection of magnetic field because of the flow. The third term is just like for vorticity, it is tilting or turning of magnetic field because of the flow, or also the stretching of magnetic field lines because of the flow. The final term is the diffusion of magnetic field because of magnetic diffusion effects. So now let us look at the Ampere-Maxwell's equations once again, just to summarize. So I have already mentioned about Ampere's law and Faraday's law. I have put the letters in red color here just to remind you that in this case Ampere's law has A, which means this equation will have a B here, and here I have a F. So the Faraday's law is going to contain a curl of E. So this is just a mnemonic. It's just useful to remember which law is which. And Ampere's law is the same as the Biot-Savart law. It's just curled, uncurled. Sometimes it's useful to look at the Biot-Savart law, because suppose you have applied current and you want to find the magnetic field because of the applied current. That is very useful in some applications which are current driven MHD applications. In that case, the Biot-Savart law is the one which is more important and relevant compared to Ampere's law. And of course then we have the div B and div J equal to 0, which is saying that magnetic monopoles do not exist, and the second one is conservation of charge. So current flows in the closed loops, and then we have the same Ohm's law that I mentioned earlier, induction equation now with the magnetic diffusivity, and then solving this induction equation, which is derived by looking at the Maxwell's equations, the Ampere-Maxwell's equations and Ohm's law. We don't need to solve any of those equations. If you solve the induction equation in our computation, that is generally equivalent. But this equation also is a nonlinear equation. In case you not noticed, there are two terms, u dot grad of B and B dot grad of U. Both could be nonlinear. So it's a complex equation just like Navier-Stokes. So not always easy to solve it. Especially if you're solving it in conjunction with Navier-Stokes, there are a lot of variables involved. So it is this Lorentz force which essentially is the term important to initiate flow or accelerate the flow or retard the flow, depending on its sign. Important parameters in MHD. So magnetic Reynolds number is the ratio of the advection of magnetic field divided to diffusion of magnetic field. So that comes out to be UL by lambda. So this is one of the most important parameters. And the second most important parameter is also called the Hartmann number. So it's basically the square root of the Lorentz force to the viscous force. So that is the terms in the Navier-Stokes equation which are involved here. Whereas in the first equation it was the terms in the induction equation which gave me this magnetic Reynolds number ratio. And then we can also define interaction parameter, which is nothing but the ratio of the Lorentz force to the inertia force. We also have something called magnetic Prandtl number. Since we have a magnetic diffusivity which has the same dimensions, the ratio of these two is called magnetic Prandtl number. And we have a couple of parameters called alpine velocity. It has a dimension of velocity, interestingly. And then we also have something called magnetic damping time, which has the dimensions of time. But if you see the ingredients, is basically density divided by rho b square, which if you apply the right dimensions, which you should do and cross verify, it gives you the time scale of magnetic damping. So it's called damping because the Lorentz force is typically a retarding force. If you recall the example that I gave in the initially mutual interaction of U and B, there the Lorentz force was opposing the moving conductor. So typically that is one behavior that is a classic of MHD, especially MHD at low magnetic Reynolds number. So that's why the magnetic damping time, the word is used, because the magnetic field can damp the velocity field through the Lorentz force. Now, what is the inductionless or the potential formulation? Now, in applications such as liquid metals and their flows, which are not too high speed flows, in those applications, it so happens that the magnetic field does not change much with time, and in those cases, the induction equation, the full form of the induction equation, is not necessarily required. So you may only need some parts of it. For example, the diffusion part of the magnetic field will be required, the Laplacian of B equal to 0, in case you want to find the static field distribution. But if that is not required, then the entire induction equation is not required to be solved. Now that is a big advantage, because it's one less equation, but it's many more variables which are sort of reduced, and that lowers your computational complexity. So in those cases, the equations get decoupled. So what I mean is that the Lorentz force that is required in Navier-Stokes. Now in classic case where the Rm is not low, in that case I mentioned that you need a Lorentz force. A Lorentz force requires J and B, which are both non-zero, and they should not be parallel, which requires essentially to compute the Faraday's law and the Ampere's law and Ohm's law. Essentially, I'm talking about the induction equation being solved together to supply a Lorentz force, which is required for Navier-Stokes, and this gives us velocity field, which is further required in this particular part of the Ohm's law, which is essentially what gives us the induced current, and therefore this is fully coupled, two-way coupled. Now, if equations become decoupled at low Rm, in that case, you do need a Lorentz force in Navier-Stokes equation, definitely, but that only requires us to use the Ohm's law, and in this case, the velocity field is certainly required in the Ohm's law, which gives us J, which gives us Lorentz force. But if you look at this coupling compared to the left hand side, the Faraday's law and the Ampere's law are not required. So that is one simplification which can happen, and in that case we only need Ohm's law, which you can rewrite with the help of electric field and div J as this Poisson's equation. So it is this Poisson's equation which is required to be solved in those situations. Now it may so happen that sometimes both the current and magnetic field are constant. In that case, the equations are even more decoupled. So in that case, we don't even have a requirement to update the current because there's no U cross B, or if it's very small. That makes the computation much more simple, but of course it's only valid in some specific situations, and only for those cases we can make this simplification. Now some applications of MHD. Now some engineering applications first. Now, aluminum production, as you are aware that the cost of aluminum got reduced drastically because of the famous Hall-Héroult process, in which a large amount of current is passed between these two layers. So essentially cryolite is the aluminum ore, and the pure aluminum essentially drops because of being heavier, right? And there is a liquid-liquid interface here. Now, any small perturbation in the interface because of whatever reason, such as removing one anode or creating some movement, that means some extra current is drawn in some locations, and that extra current, you can think of it as a small j, which will produce some Lorentz force which can make this interface more oscillatory or more unstable. Now that is not ideal, because you will want to avoid any short circuit possibility at all cost, because that is too dangerous, and you would also not want to make this particular layer very thick, because it's the layer of lower conductivity, so you have a lot of losses happening there. So it's a classic optimization problem in that sense, and a lot has been done to sort of arrive at some do's and don'ts of what to do to keep the instabilities on the minimal side. The other application is continuous casting of steel, where the application of magnetic field is required sometimes to retard the flow. So sometimes some very high turbulence near the top part can suck some air or gas, and it can be like an inclusion which will make the steel quality bad. So in that case, what we need is a magnetic field to retard the flow, and sometimes we need to enhance the motion, especially downstream of the continuous casting process. Sometimes the magnetic field, and in this case an alternating magnetic field, is used to create what is called as electromagnetic stirring, where if you see in this figure D, we have a magnetic field present, and the figure A has no magnetic field. So this streamlines show you the swirl which can be created with the help of magnetic field, which is called, this process is called electromagnetic stirring or EMS. The top was called EMBR or electromagnetic braking. One of the application is liquid metal battery, which is also what we are working on. Here this application is very promising from the energy storage point of view. So here we have 3 layers, and all these are liquids. There's a negative electrode, there's an electrolyte in the middle, and there's a positive electrode. The negative electrode is typically a light metal like sodium, magnesium, lithium, and the large current, and the current passes here, which will ionize this, and it will go to the bottom electrode, and that will leave some electrons to flow in the outer circuit, which we can use to power our devices. And the opposite happens when the battery is being charged. So in that case, the ions go back and join the negative electrode. Now, liquid metal battery is a very interesting concept in a sense that it can be made with potentially very cheap materials. It can be made in a very safe and reliable way. It can last very long. So it's very promising, and a lot of work has been happening to improve these advantages and to mitigate all the disadvantage of liquid metal battery. Now, as you have noticed that there are 2 liquid-liquid interfaces here. So in this case, what you see here happening on one interface may happen on both interfaces. So it's a classic engineering optimization problem once again. Apart from this, it may also have other phenomena such as thermal convection and the convection because of the concentration gradients, which can also arise. So this figure shows you this similar schematic that I showed you earlier. It shows you the diverging current and converging current in the 2 different layers, because of which the electrovortex flows or the current driven MHD flows can arise. So going to this geophysical example, so we are sitting at the Earth's surface. Now around 6,500 kilometers below us, we have the liquid outer core of the Earth, and it is hypothesized that the magnetic field that we can measure with our magnets essentially arises in that liquid outer core. Now exactly how this happens, no one really knows, because it's difficult or almost impossible to make any measurements. So people have done a lot of theory and numerical simulations. Now it is thought that the flow of liquid iron and in the presence of the Earth's rotation and in the presence of the buoyancy because of the thermal gradients and the concentration gradients, the combined effect of that is what creates and also sustains the magnetic field against the decay. So it has been reproduced very nicely in some classic simulations, and in fact the simulations have also shown that magnetic field can potentially reverse. So the north can become south and the south can become north This happens every 300,000 years. People say that one reversal is now due, but thankfully this doesn't happen very fast. And I think it's not a good idea, because I think a lot of our devices are actually dependent on the nicely dipolar magnetic field. Now, one question which interests fluid dynamicists like me is that how does the motion of liquid iron, which is thought to be quite turbulent, because the dimensions are very large and the kinematic viscosity of liquid iron is quite small, so it's thought to be highly turbulent. How can that highly turbulent motion lead to a nicely organized dipolar magnetic field? That's a very interesting question, which has interested researchers for almost 100 years and more. I showed you this picture earlier where this is Earth, our planet, and its magnetic field, and this magnetic field essentially protects us from the harmful effects of the solar wind. It's possible to predict the solar wind, though. In fact, we have some measurements also which are coming in as we speak. The Parker's solar probe and our own Aditya solar mission, they are all gone into this region to take measurements of the magnetic field. A lot of simulations and theoretical work has been done for this particular case also. In fact, the shape of this what is called as a CME, or coronal mass ejection, it was theorized by the scientist called Eugene Parker, in whose name this Parker solar probe has been sent by NASA. So this is another image showing you this curved field lines. I think this is maybe obtained with the help of some actual data that has been captured. Now, interestingly, a lot of data exists about the sun, but not so much exists about our old planet, because of the fact that this is vacuum, so it's possible to make measurements, even though it's not very close. But the mantle and the outer core are quite far, especially outer core is very, very far. It's very difficult to dig and do any drilling and go to the outer core. Almost impossible once again. Now let us look at this solar flare, or this coronal mass ejection, a movie of that, and this loop is called the loop of the solar flare, the loop of the coronal mass ejection. This loop essentially shows you the magnetic field lines, which changes quite fast, by the way, and this artist has also put the Earth here as a small circle, just to show how small we are compared to a small loop, small magnetic field line loop on the sun's surface. So this is the ITER schematic I showed earlier, and here there are two ways the magnetic field is involved. So first of all, it's involved in confining this plasma, which is at a very high temperature. So magnetic field is used to confine that, and the other application of MHD is in the liquid lead lithium blankets, which is a liquid metal at a very high temperature, and that is basically there for three purposes. It's also there for cooling, so removing a huge amount of heat. Remember that plasma is very, very hot and almost like sun kind of temperature, and the magnets, which are almost cryogenic temperatures. So look at the temperature gradients involved here. So a lot of heat has to be removed. It also serves the purpose of breeding tritium, which is an important ingredient in nuclear fusion, and finally it also serves as a shielding material for the radiation. So this is being built, and there's some success recently. I think they are waiting for the time where they are able to produce more energy compared to the energy that has been put in. If that happens, then of course from there they will think about some applications, and some realistic reactors might be built. This is still an experimental reactor, and it's a nice collaboration between several countries. In case you are interested, you can search about this. Some more applications are mentioned here. I will not go into the details, but a couple of pictures on the right hand side. So for deep space applications, it's difficult or almost impossible to use the rockets because chemical fuels will of course run out. So in that case, if we have a way of getting some energy from the sun, we can use that and store it in a battery, and if we can use that to propel some electrons from the cathode to the anode, that effect will create some sustained propulsion. It will not be a very large force, so we don't need large thrust. What we need is a small thrust for a long sustained duration in deep space. So that is one idea which has been there, and I think some MPD thrusters are already built and being used. The marine propulsion is something which was tried by Japan, and even a ship was produced. So as shown you in the bottom, it didn't take off because of the fact mainly that this is to be deployed in the sea. So seawater is conducting certainly, but the conductivity is still much less than liquid metals. So remember I said that in MHD you need to have the electrically conducting liquids, and that is very important. So low conductivity liquids are not very good candidates for any MHD effects. So apart from that, there's a list of some references, and with that I would like to end. And if you have any questions, I will be very happy. Okay, so let me go through this last slide. Yeah. So these are some references. In case you notice, there are 4 textbooks that I have mentioned. And the second one is a textbook which is a bit old, so you may not be able to find it somewhere. But the other 3 you may be able to find it. And I don't want to give you ideas on how to find it. I think you know what I mean. Yeah. So any questions, any comments, anything is okay. You can just feel free to unmute and ask the question. If there are any questions in the chat box, Ms. Payal, would you mind reading that to me?
Yes. We had a question from one person, Sharifuzzaman. He was
Yes.
asking, sir, do you do any experimental on MHD along with CFD simulation?
Yes. So experiments are certainly very interesting ways of studying any phenomena. And we have started doing some experiments, but not yet with liquid metals. So we have been doing some experiments with conducting water. So adding some salt to water makes it conducting. But you need a very strong magnet to have any MHD. So I remember I said that you have to have sigma, which is a conductivity, and you have to have the magnetic field. So if the sigma is small, then you have to kind of compensate for that by increasing the magnetic field. So for that we need strong magnets, and strong magnets are not easy to handle. We have to be very careful in handling. So we have been doing some experiments with strong magnets. The other option is to use electromagnets. In case you have heard about Helmholtz coils, some people also do experiments with the help of Helmholtz coils. So we have not done any experiments with liquid metals as of now, but there is a plan of starting to do some experiments with liquid metals also. Simulations, we have done plenty of simulations for a variety of geometries, and both applied magnetic field and applied current simulations we have tried with OpenFOAM, and also with some softwares like COMSOL and ANSYS Fluent.
Okay, any more questions? Please carry on.
Hello, sir.
You can unmute yourselves. Yes.
Give you one example how to relate the Navier-Stokes equation with all the criteria.
How to relate the Navier-Stokes equation with
all your criteria, like you give in one slide the how to connect the Ohm's law or some Lorentz law with the Navier-Stokes equation.
Yes.
So I'm not getting the relate how it is possible.
Yes. So the question was about the Navier-Stokes equation, which you see at the top, and it's about Ohm's law. I think it's about in general the electromagnetic equations. So if you see the equation, the term that I draw a circle on, this is a term which is sort of a new term in the equation, because apart from that, this equation is what we already know in as a vector form of momentum equation, right? Now in this, there are 2 quantities, J and B, and J is what is called the current density. So it's basically, you can think of the J magnitude is current I by area. Okay. Now B is the magnetic field intensity, or also called magnetic field, and for that we need all of these equations. So these are all called Maxwell's equations. This term Maxwell's equations is actually for whatever you see here, and we also need Ohm's law. So this is Ohm's law. Now clearly it's a lot of equations that is required to be solved, and that may seem a little bit daunting and intimidating. That is why some people want to derive a compact equation, which they call it the induction equation, magnetic induction equation, which is just a different way of writing all of these equations here. So all the Maxwell's equations plus Ohm's law. There was a slide where I showed you what are the different steps involved to obtain the induction equation, which I said looks exactly like the vorticity equation. Okay, so in that case, you only need to solve the Navier-Stokes and induction equation. That's it. So that was the yeah. And the other thing I mentioned was that some of these terms, for example, this term is not required in MHD because of some approximations. This term is also not required in MHD. Similarly, here also in the charge conservation, yeah, this equation is not required to be solved. So this goes away. So that's why, if you recall, I said that you can. So the list of MHD equations I mentioned looked a little bit simpler compared to what we saw just now. Okay, so this is a list of MHD equations which are required in a sense either directly or through induction equation. It is like a combined form of this all the top equations. So essentially this entire thing combines to give me induction equation. And this induction equation plus which includes Ohm's law, induction equation plus this Lorentz force as a body force term in the Navier-Stokes is what I require to understand full MHD. So in case you don't need to do full MHD, for example, in some cases, all the terms need not be solved. So that's called as a low frequency or low RM approximation. So in that case, the equations become much simpler to deal with. So if you want me to elaborate on that, I can do that. But I hope this answers your questions at least partly.
Yes, sir. I got it.
Yeah. Any more questions?
Sir, Arpita has one question written in the chat box. I
Yes.
read it for you.
Yes.
How is the Hall effect ignored and what are its implications?
Yes. So Hall effect is essentially what is called as an E cross B term. So that also leads to an EMF generation. So in case there's a low frequency approximation involved, which I mentioned here, this low frequency approximation, just like this low frequency approximation, helps me ignore the second part of so this Ampere's Maxwell equation has two parts, the top and the bottom, as I mentioned. So from low frequency approximation, we can show that this part in the top is much greater than this part at the bottom. That's what was the purpose of this slide. Now, in the same way, this Hall effect term, which is essentially because of the E cross B. So if electric field and magnetic field are both present and they are not parallel, that leads to an extra EMF generation. And that's what is called as a Hall effect. Now, in the low frequency approximation, we can ignore this E cross B contribution as compared to other contributions like U cross B, induced current, and the applied current contributions. So it's just a low frequency approximation, which once again helps me. Now, in some cases, it's not possible to ignore that. Sometimes we want to have the Hall effect, and in fact, the current because of Hall effect is the main driving force. In those cases, we don't ignore Hall effect. But in typical examples of MHD like liquid metal flows, it is common to ignore Hall effect. So there's something called Hall effect thrusters, which is also a device for space propulsion. So there, the Hall effect is not ignored because that is the cause of the force that is required. So, any questions on applications or non-dimensional numbers or potential formulation? So potential formulation is something which I mentioned, and in case people want to work on some engineering applications of MHD, the potential formulation is something which I think makes the subject also quite easy as compared to the fully coupled situation. Now, is it the case that in all engineering applications we can make this assumption? So that is not true. We can make this assumption of the equations becoming decoupled, and you only need Navier-Stokes with Ohm's law. That assumption is useful in many applications, but in some engineering applications, so let me tell you one example of an application. Like in the continuous casting of steel, here also the length scales are very, very large. So this is what is a liquid steel, and this is an interface, and there's a magnetic field applied, which essentially dampens the motion of the molten metal coming in and This can become very turbulent at times because of the fact that the velocities are large typically, and then the length scales are large, and the kinematic viscosity of liquid steel is also quite small. So all of that makes the Reynolds number, the classic Reynolds number, very, very large. It also makes the magnetic Reynolds number large. So there, once again, we may have to solve the full MHD equations rather than only the low RM formulation. So that is one example. And of course, when we go to this geophysical and astrophysical examples, like core of the Earth, here also the full equation for MHD, including the buoyancy force, including the Coriolis force because of Earth rotation, the entire equation has to be solved, and it has to be solved in spherical shell geometry. So because the geometry of the outer core is a spherical shell, so that is somewhat complicated. But yes, geophysicists do that. It's quite routine nowadays, but it's very heavy computation. So computations are typically quite computationally costly. And similarly, so here also RM, the magnetic Reynolds number, is of the order of 1 or around order of 10. So it's not very small compared to 1. Nobody knows exactly what is the magnetic Reynolds number because we don't have an exact idea about what are the typical characteristic length scales and velocities. We only speculate about them. On the other hand, we have a pretty good idea about what is happening and at the sun's surface and what are the velocities involved there. What are the velocities involved in the solar wind, for example. So this is our planet Earth, and this is like a cartoon drawn by some artist. But this magnetic field lines are not very far from what is actually there. So here again, in solar wind, maybe at some locations low RM approximation may work, but typically it is not at all low RM. In fact, very, very high, quite high magnetic Reynolds number. And sun's surface, definitely a very high magnetic Reynolds number. So sun surface, the magnetic field lines are very complicated. In fact, if you see a particular loop, this is basically rising from a north pole and falling on a south pole. So on the sun surface, we have many pole pairs. It's not a single north pole and south pole like we have on the Earth. It is quite complex and multipolar. In fact, if there are interests among people, you can look at the theory of sunspots. So there's something called sunspots, and every 11 years, there's a certain pattern which repeats in the sunspots. And one can predict what is going to be the sun's surface in ahead of time also because of simulations and because of this knowledge that we have gained about the activity on the sun. If you have any questions or comments, anything, you can just feel free to ask.
So the thing is, when we talk about validation in any flow or anything while doing CFT,
Yes.
how do we know what we are doing in this MHD is right or wrong? How do we validate what we are doing?
Yes. So we cannot validate with any experiments. For example, with for the Earth's.
No, not about the Earth, but normal,
yes,
simple like electrolyte and everything that you were talking about.
Yes. So there are some experimental data is available, not all in realistic geometries. So I think for each of the applications, including, I think except liquid metal batteries, for each of the applications, people have done some simplified experiments. For example, with this aluminum production, people have taken 2 different liquid layers, and since you know about non-dimensional numbers, you can design your experimental setup such that the dynamics which you see in your model is also what you may expect to see in the actual scenario, right? So in that case, lab experiments are definitely possible, and there is some data, but data is very scarce. The reason is that in classical fluid mechanics, because you use air and water most often as your experimental fluids, you can make a lot of intrusive measurements with the help of your PIV and other stuff. Now here, typically all the conducting liquids, like liquid metals, are opaque. That means it's very, very difficult to make almost impossible to make any measurement with PIV because optics doesn't work in opaque liquids. We can use something called UDV, ultrasonic Doppler velocimeter. We have that in our department here, and we have been using it not for liquid metals yet, but we plan to use that. But the difficult thing about that is it only gives you the velocity on a particular line. So it works like the LDV, laser Doppler velocimeter, in the same way, but here it uses the sound waves. Now sound waves can travel in the opaque liquids also, and so they travel, they reflect back, and the shift in the velocity, the phase shift, is what is recorded and converted to velocity. But the limitation is it only gives us the velocity on a particular in a particular line. So we need a lot of Doppler UDV velocimeters to get like a full picture, which is where simulations are a very, very big help. So yeah, so but there is some data, but very, very scarce data. In fact, we also struggled with finding data to validate our open form simulations. So it's a major issue.
And then what about the liquid metal batteries? You were talking about something about that.
So liquid metal batteries, there is no measurement available on the exactly for the battery configuration, but there are some measurements available. For example, let us say if we take this top gray part, this is one electrode. So current entering from a smaller area to a larger area. So there are some experiments which have been performed in this configuration, where people have studied electrovortex flows, and people have also studied some other phenomena, again with the help of UDV and some similar devices. So we have some line measurements available and reported in literature. Some are from the early, or I think around 80s, early 90s, and those are what we used for validation. Some recent experiments also done in China and in Germany. So Germany, there's a group in Dresden. It's called HZDR, Helmholtz Zentrum Institute in Dresden. They are the one of the world's leading group in the entire MHD. So in fact, they have worked on almost all aspects of MHD. So they have a very good facility also for making some fantastic measurements. So if you're interested in what kind of experiments they do, you can look at their website. In fact, they also create a mini dynamo, like a small spherical shell kind of I think that is also there in America, in Johns Hopkins or Maryland. I think Maryland. But yeah, so difficult to do experiments, but people have tried. Also very expensive and I mean very difficult to get funds to do experiments for fundamental stuff. But yes, liquid metal batteries, I think we need more experiments, and hopefully, I think with time we'll get some more data.
Thank you.
Okay, so I think seems to be no more questions. So, right, in that case, I will stop sharing, and maybe Swapnil can start sharing his screen, and then.
Yeah, sure. Thank you, sir.